First question is state Newton's law of gravitation in words. What we have, there are 3 points we have to make. The first one is that gravity is an attractive force. The second point we have to make is that it's proportional to the product of the two masses. And the final point we have to make is that it's inversely proportional to the squared distance between the bodies. Okay. And an important point being that it's the distance squared between the centre of the two bodies. Second question we have is to show that t squared is proportional to r cubed by equating central force and the force of gravity. So start off with central force is equal to the gravitational force. So the central force acting on, we have a large body m and a smaller body little m that are separated by some distance little r, and this object has orbital period omega. So what we have is little m times r omega squared is equal to the gravitational force, which is g Newton times big M times little m over r squared. The little m's cancel, so we get omega squared is gm over r cubed. Omega is equal to 2 pi times the time taken for a full orbit, which gives us 4 pi squared over t squared equals gm over r cubed, which gives t squared equals 4 pi squared over gm times r cubed, which shows us that t squared is proportional to r cubed. The third question is to calculate the length of a year on Mercury, given the distance between the Sun and Earth and the distance between the Sun and Mercury. So using the rule we've just found, t squared is proportional to r cubed, we have the time of an Earth year squared divided by the time of a year on Mercury squared is going to be the orbital radius of Earth cubed divided by the orbital radius of Mercury cubed. So what this means is that Earth, if we measure time in days and orbital distance in meters, we have 365 days squared divided by how long a year is on Mercury. That's what we're trying to calculate. And this is equal to the orbital radius of Earth, which is 1.5 times 10 to the 11. Then we cube that and divide this by the orbital radius of Mercury, which is 5.79 times 10 to the 10, and then we cube that. If we rearrange this, we get t Mercury squared is 1.5 times 10 to the 11 divided by 5.79 times 10 to the 10. Cube the whole thing. Mercury squared is 5.79 times 10 to the 10 divided by 1.5 times 10 to the 11. Cube the whole thing, multiply by 365 squared, which turns out to give t squared is equal to 7662 point something, which gives a year on Mercury is equal to 87.5 Earth days. Okay. The last question is to calculate the ratio of the distance from the Sun to Neptune to the distance from the Sun to Earth. Just clean this up. So, let's say big R is distance from the Sun to Neptune divided by the distance of the Sun to Earth. So if we work out big R cubed, this is going to be R Neptune cubed divided by R Earth cubed. And from our previous discussion, we know that this is going to be equal to the square of the ratio of the two orbital periods. So we have T Nep squared over R Earth, over T Earth squared. And the orbital period of Neptune is 165 Earth years, and the orbital period of Earth is just 1 year. So that means R equals 165 squared to the power of 1/3, which means R is 30.1. And that's the final question.